Hello everyone, welcome on this e-learning platform of Apex Institute of Physics. In this video we will talk about electric potential due to a uniformly charged spherical shell. So let's say we have this spherical shell which is uniformly charged, and the total charge is Q, that is on its surface, and there's no charge inside it. And let's say the radius of this sphere or spherical shell is R. Again, just like an electric field, we will find the electric potential both inside the cell as well as outside the cell. Now let me recall for you what the fields used to be. Inside field used to be 0 if you remember the previous videos, and outside field, because of a spherical shell, used to be the same as due to a point charge, that means kq upon r square. So these were the electric field formulas for uniformly charged spherical shell. Here we are not going to find this electric field, rather we are interested in electric potential. So we will see how the electric potentials are going to be inside as well as outside. So let's say we talk about first a point which is lying outside. So which is, let's say, from the center at a particular distance small r, and that location point is P. We are interested at point P, the potential, because of this charge distribution. We know the potential at any point is given by V is equal to minus integration running from reference in infinity to that location P. Integration is of this dot product, which is E dot dr. This was the basic formula that we have derived earlier. Now if we are interested in outside point, so this P point will be lying outside. If we are interested at inside point, so this P point will be lying inside. So let's talk about this outside point first. So outside, when we say outside, we refer that R is greater than capital R. So P point is outside as shown here. Now we know outside the field, as we just recalled, E is equal to K Q upon R square, and we know this is R cap direction. This field is just like a field because of a point charge. So the influence of this sphere for outside point is same as that of point charge, and potential is running from infinity to that location P. So if we move from infinite location somewhere to point P, in all the way we will be finding the same field as due to a point charge, and same for this spherical shell. Hence we can claim theoretically that at P point the potential will be same as that due to a point charge. We can mathematically prove it here as well. And so this is E expression outside. Another term that we need to know is dr. Dr is equal to dr magnitude in r cap direction. Now after let's simplify this formula. So this V will become equal to minus integration from infinity to that P point, which is indicated by R. Field is KQ upon R square, and then that is dr, and in the bracket we will find r cap dot r cap. We know this unit vectors dot product is unity, that is 1. So this will become equal to kq within the bracket 1 upon r after integration. We had this integration earlier as well. 1 upon r square will lead to minus 1 upon r, and minus in minus will become plus. This has to run from infinity to that location which is r. So potential at inside this outside point is coming as kq. Once we are placing small r as r, another time we will replace this small r by infinity, so 1 by infinity will become 0. So ultimately it will become this, which was expected as per our theoretical interpretation. So this potential is just like due to a point charge, and it was expected as so because the field outside remains same. Now similarly we can work for inside point. When we are working for inside point, so this P point has to be opted inside, that means R becomes less than R. Now we know if we have to carry this integration up to inside point, let's say this time the point is somewhere here and this location is R, this is new point P for the second case. So integration will be in this manner: v is equal to minus from infinity to that location P, or location R rather, inside E dot dr. There are rules for integration that you will learn in mathematics or basic maths for physics. So this integration can be divided into two parts, limits running from infinity to, let's say, capital R location, and then E dot dr, plus from capital R to the inside point E dot dr. We are making this integration into two parts because of a reason. You can think about the reason. The reason is the field inside is different. This is going to be the field for inside part of this sphere, because here the distance is running from capital R to small r, that means we are inside part, and this E will have expression for outside. So this is for outside and that is for inside. Now since both have a different formulas, hence we are segregating into two parts. Now if we carry it forward, so we know this inside field is 0. So this second term will not be anymore there, and this will be left with the only first part. And if we simplify this first part, so this will become equal to minus integration from infinity to capital R E dot dr. Now this E is for outside field, and we know outside field is k q upon r square r cap and dot dr vector, which is going to be dr r cap. This integration is exactly same as we had just finished in for outside case. The only thing is upper limit has, in this case, is going to be capital R. So in final result we can replace a small r by capital R. So this will lead to k q upon capital R. Hence we found the formula for outside point is kq upon small r, and for inside point v is equal to kq upon capital R. So this becomes the formula for inside point. So let's say put it in a bracket. So this is field for inside point. Now let's interpret it. What type of the fields are we are getting? This is scalar field, that is potential. This formula is for outside point, which is 1 upon r. This formula is for inside point, which is independent of small r. Since it is independent of small r, so we can say inside potential is constant. That means the potential at all points is has the same value, and that value is kq upon capital R. This is also a value on the surface. So on the surface and inside potential remains constant, whereas outside it decreases to 0 at infinite location. The same result we can interpret in graphical representation as well. So let's see how it looks like in graphical representation. So let's summarize here the entire result. Electric potential due to spherical shell, we got to get as V is equal to K Q upon capital R for inside point when R is less than or equal to capital R, and we got V is equal to K Q upon small r when R is greater than or equal to capital R. So this is for inside point, this is for outside point. In graphical representation it looks like this. This is the origin, that means center point, and at the center point the potential will be kq upon capital R, and this potential remains constant all through till the capital R. That means we are on the periphery or on the surface. On the surface it remains same from both the sides, so it's a continuous. Later on it follows 1 upon r. 1 upon r graph is called a rectangular hyperbola. So that's a straight line, that's a rectangular hyperbola. So if somebody asks what this curve is known as, so we can call it as a rectangular hyperbola. and the first part, that means inside part, we can easily see is a straight line. So this is graph of potential of spherical shell. Spherical shell. This is quite important for exam point of view. It is often seen in the examinations. So we need to remember this is for spherical shell, that too which is uniformly charged. Uniformly charged. And of course this is non-conducting we are talking about. In conductors we will deal them separately. So these are formulas for potential, and this is a graphical representation. Now we will be talking about the electric potential due to a solid sphere which is non-conducting in nature and uniformly charged. So here is the next part, which says electric potential due to a uniformly charged solid sphere. So let's say we got a solid sphere which is having a uniformly charged distribution, or total charge is Q, and radius is R, and the charge is distributed inside as well as outside, so that is solid sphere. Now we know the field because of this solid sphere both inside and outside. So potential, first we will talk about what the potential outside is. So outside means where R, the distance from the center, must be greater than the radius. That's what the outside point is. Now the potential as per the formula is minus integration from infinity to that point outside R, E dot dr. And we have understood earlier, and we know that the field outside of a solid sphere is same as due to a spherical shell or point charge. That means E is equal to K Q upon R square R cap. Now we have used the same field for point charge and just earlier for a spherical shell, and we had the same this expression to integrate. So if we borrow the calculation from there, we can say the potential is going to be equal to K Q upon R. So outside the solid sphere, the potential is going to be equal to V is equal to KQ upon R. So that's the result for outside. Now we can find out the potential for inside point. So let's talk about the inside point. In case of inside, we know this small r, which is measuring the distance from the center, going to be less than as compared to capital R. That means it is inside this solid sphere. And in this inside part, the field has a formula E is equal to K Q small r divided by R cube. By now you must have understood it, and you must remember this. And R cap, if we merge this R cap with R, so that becomes R vector. So this is the field which is different than the field outside. Hence we will get a different expression for the potential inside. So this will lead to the potential expression as V is equal to minus integration from infinity to R. First we will integrate up to R in two parts as we had in the spherical shell case. So E dot dr. In this case the field will be used for outside point, then minus integration from this capital R to small r. That means second part, this will be using the field which is inside. So here we are using two expression for integration. One will use the field from outside, and another will use the field from inside. Now to carry forward this integration, we will say V is equal to minus, or let's talk about this first integration. So whatever this first integration is, that is using the field existing outside this solid sphere. So this will have the same expression as the field just outside. So in this expression, if we replace small r by capital R, because the limit is now capital R, so this will become the value of the first part. So first part is from outside field, hence this integration will have value k q divided by capital R minus. Now the second integration will use the field that we have listed for inside part. So let's place there. So it will go from capital R to small r e. This new e definition will be k q upon r cube, and this r cap and dr, they will combine together, so we can write as r dr, and in bracket r cap dot r cap. Again r cap dot r cap will become unit, that is 1, and this integration can easily be performed. So let's move ahead and perform that integration. So first term kq upon r is as such, minus, from the second we can take the constants out, which is kq upon r cube. These are the constants, and integration will be of r dr. We know r integration will lead to r square by 2. So this integration is going to be r square by 2, having limits running from capital R to small r. Now further simplification will lead to v is equal to, we can take something let's place this limits first. So this is going to be kq upon r minus kq upon 2r cube, within the bracket is going to be r square minus r square. Now this is the answer. We can rewrite this answer in a different format as well. We can take this kq upon 2r cube as common. If we take this as a common, so first term has to be multiplied by 2, because we have divided by 2, and r square, so it will left as 2r square, minus, this minus will go inside, so it will become minus r square plus r square. So inside the bracket we will get the 3 capital R square minus small r square. So we will get a formula v is equal to k q upon 2r cube, within the bracket 3r square, 3 capital R square minus small r square. It's a little bit complicated, but it's important result that has to be understood and practiced to remember. So this formula is for potential inside the solid sphere. This formula is for potential outside the solid sphere. Now some important thing that we can think about here is if we talk about at center, so here at center the potential will be calculated by placing r equal to 0. If we substitute small r equal to 0, then this term will become 0 and r square will get cancelled out, so v will turn out as 3kq upon 2r square. So at the center of solid sphere potential is 3kq upon 2r square, and at inside at any point it is this, and outside at any point it is this. We can also interpret the same result in graphical way, so let's do that as well. So let's summarize the potential because of a solid sphere. So formula wise, v is equal to k q upon 2r cube, within the bracket 3r square minus r square. This is for those points which is inside the sphere, that means r is less than equal to capital R, and v is equal to kq upon r for all those points which is outside the solid sphere. And here is the graphical representation. This is origin, and as we have calculated earlier, the center the potential is 3 by 2 k q upon r square, and this is a surface point. On the surface, r has to be placed by capital R. On either of the two, we will find kq upon capital R. So at this point, this is on the surface. If you look at the surface, so this point will have a potential kq upon capital R. So that means the potential at the center is the maximum. It decreases parabolically because it's r square, and on the surface it becomes kq upon r. Then after it decreases rectangular hyperbolically, so that is parabola. If it is being asked what type of the graph it is, so you say that's a parabola, and we know this is a rectangular hyperbola, as same as in the case of this spherical shell. So this is an important graph, and these are the important results that we have talked about: the potential at the center, on the surface, and all other points. Well, so please keep on revising and making the notes, and keep on following. Thank you for watching. Have a good time.